Welcome back. In this lecture I shall discuss centrifugal compressors. The specific objectives of this particular lecture are to describe the working principle and constructional features of centrifugal compressors, present an analysis of steady flow compressors and define polytropic efficiency, establish relationship between power input, pressure rise and tip speed. So, at the end of this lesson you should be able to explain the working principle of centrifugal compressors, carry out thermodynamic analysis of steady flow compressors, and establish relationship between impeller speed, diameter and power input and pressure rise. Let me give a brief introduction. As you know, centrifugal compressors, also known as turbo compressors, belong to the rotodynamic type. In these compressors, the required pressure rise takes place due to the continuous conversion of angular momentum imparted to the refrigerant vapor by a high speed impeller into static pressure. Unlike reciprocating compressors, centrifugal compressors are steady flow devices, hence they are subjected to less vibration and noise. Now let me explain the constructional features of a centrifugal compressor. You can see the side view and the front view of a centrifugal compressor. Refrigerant enters like this, and this portion, if you look at this, this is the inlet, refrigerant inlet. This is also known as eye of the impeller. So refrigerant enters like this and then takes a 90 degrees turn and enters into the blade passages of the impeller. These are the impeller blades. So the refrigerant flows through the passages provided by these impeller blades, and these impeller blades will be rotating at very high speed, as a result of which momentum will be imparted to the refrigerant when it comes in contact with the impeller blades. So from the impeller it enters into a region called diffuser, that is 4. Okay. In the diffuser, conversion of velocity pressure into static pressure takes place, as a result of which its velocity reduces and the refrigerant pressure increases. And from the diffuser it enters into a volute casing. You can see that the volute casing has uniformly gradually increasing area. So as the refrigerant flows through the volute casing, its velocity reduces gradually and velocity is converted into static pressure. So finally the refrigerant comes out of the compressor at high pressure. So once again you can see the how the refrigerant flow is taking place and different parts. As I said, part 1 is the refrigerant inlet and part 2 is the impeller. 3 is the refrigerant passages, so these are the refrigerant passages, and 4 is the vaneless diffuser, this is the vaneless diffuser, and 5 is the volute casing, and 6 is the refrigerant discharge. Now let me explain the working principle. Low pressure refrigerant enters the compressor through the eye of the impeller. Eye of the impeller is nothing but the inlet of the impeller. From the eye, the refrigerant enters the flow passages formed by the impeller blades, which rotate at very high speed. That means the impeller will be rotating at very high speed. As the refrigerant flows through the passages towards the tip of the impeller, its angular momentum and static pressure increase. From the tip of the impeller, the refrigerant flows into a stationary diffuser. In the diffuser, the refrigerant is decelerated, and as a result the velocity pressure drop is converted into static pressure rise, thus increasing the static pressure further. The vapor from the diffuser enters the volute casing, where further conversion of velocity into static pressure takes place due to the divergent shape of the volute. Finally, the pressurized refrigerant leaves the compressor from the volute casing. So this is the working principle of a centrifugal compressor. This is different from your positive displacement type of compressor, which are unsteady flow devices. Now let me explain the physics. The gain in momentum is due to the transfer of momentum from the high speed impeller blades to the refrigerant confined between the blade passages. The increase in static pressure is due to the self compression caused by the centrifugal action. I will explain what it is. And the static pressure produced in the impeller is equal to the static head, which would be produced by an equivalent gravitational column. As you can see that as a refrigerant flows through these passages and it comes in contact with the impeller blades, and since the impeller is rotating at very high speed, refrigerant will be thrown towards the tip of the impeller because of the centrifugal action. So if you look at refrigerant at this portion, it will be pressed by refrigerant at this portion because of centrifugal action. Similarly, refrigerant at this point will be compressed by the refrigerant at this point. So as a result, as the refrigerant flows through the impeller flow passages, it continuously gets compressed and its static pressure rises. That means the static pressure at this point will be less than the static pressure at this point, and this is equivalent, the pressure rise between this is equivalent to the static head obtained by a column of refrigerant of this height. Okay, this is somewhat similar to, for example, if you have a column of fluid, the fluid at upper layer will exert pressure on the fluid at the lower layer because of its weight. Okay, there the gravity is working. Here instead of gravity you have the centrifugal action. So because of centrifugal action, the refrigerant near the inlet will be pressing the refrigerant which is away from the impeller. This is what is known as self compression. So ultimately when the refrigerant comes out of the impeller, its static pressure rises because of the self compression. At the same time, its angular momentum also rises because it comes in contact with the high speed impeller blades. So the impeller blades impart momentum to the refrigerant. So these two effects take place as the refrigerant flows through the blade passages of the impeller. If the impeller blades are radial and the inlet diameter of the impeller is small, then the static head H developed in the impeller passage for a single stage is given by, that means we are assuming that we have radial blades and the inlet diameter of the impeller is small. Under these assumptions, the static head developed in the impeller H is given by simply V square by Z, where V is the peripheral velocity or also known as tip speed and G is the acceleration due to gravity. So the increase in total pressure delta P is simply given by rho G H, that is equal to rho into V square. So from this equation you can see that for a given refrigerant, the pressure rise depends only on tip speed of the blade, because delta P is equal to rho V square, and if you are fixing the refrigerant and if you assume that rho is constant, then the pressure rise is simply proportional to V square, that is the tip speed of the blade. The tip speed is proportional to the rotational speed and impeller diameter. The maximum permissible tip speed is limited by the strength of the structural materials and the sonic velocity of the refrigerant. Hence the maximum achievable pressure rise, which is nothing but which is related to your maximum achievable temperature lift of single stage centrifugal compressor is limited. So multi-staging is required for higher temperature lifts. So what it means is, we have seen from this for a simple case of radial blades and negligible inlet diameter, we found that the static pressure rise across the impeller is simply equal to rho V square, where V is the peripheral velocity or tip speed. So the tip speed, again as I said, is limited by your sonic velocity of the refrigerant, and it is also limited by the structural limitations. When the impeller is rotating at very high speed, stresses will develop, and the stresses will be maximum at the root of the impeller. So higher the velocity, higher will be the stresses. So these the stresses developed and the sonic velocity impose an upper limit on the tip speed. So that means there is a limit on V. Once there is a limit on V, there is a limit on delta P, if you are assuming that rho is constant. Okay, that means the pressure rise that one can achieve under these limitations is limited if you are using a single stage impeller or single stage centrifugal compressor. Now what is this pressure rise? This pressure rise is nothing but, if you look at a refrigerant system, it is nothing but the condenser pressure minus evaporator pressure, okay, which again in turn is related to the condenser temperature and evaporator temperature. So ultimately what it means is the temperature lift, that is Tc, that condenser temperature minus evaporator temperature of a single stage centrifugal compressor is limited by these considerations. So if the required temperature lift is high, for example, if you have a case where the evaporator temperature is very low or the condenser temperature is high, that means you have high temperature lift. That means the required pressure rise across the compressor is very high. Okay, if that is the case, then the required tip speed with a single stage compressor could be very high, and it could be higher than the upper limit. In such cases, we have no option but to go for multi-stage compressors. Okay, single stage compressor will not work. In multi-stage centrifugal compressors, the discharge of the lower stage compressor is fed to the inlet of the next stage compressor, and so on. In multi-stage centrifugal compressors, the impeller diameter of all stages remains same, but the width of the impeller becomes progressively narrower in the direction of flow as density increases progressively. That means when you have a multi-stage compressor, let us say 4-stage centrifugal compressor, all the 4 stages will have the same impeller diameter. Okay, but since the second stage the refrigerant pressure will be higher compared to the first stage, that means in the second stage refrigerant density will be higher. So if you from the continuity equation, you know that the cross sectional area has got to be reduced. Okay, so only way of doing this is to reduce the width of the higher stage impellers. That means the first stage impeller will have a higher width, and the second stage will have slightly lower width, and the third stage will have still lower width, and so on. Okay, that means the blades become narrower as you move in the direction of the refrigerant flow. The blades of the compressor are either forward curved or backward curved or radial. That means in principle you can have either forward curved blades or radial curved blades or backward curved blades. In the older machines mainly backward curved blades were used, but nowadays the modern trend is to use radial curved blades. The stationary diffusion can be vaned or vaneless. I have explained that you have a component called diffuser. This space is called as the diffuser, as you can see 4, and here this is a vaneless diffuser. That means it is a simple empty hollow ring where you do not have any vanes. Okay, so this is a vaneless diffuser. You can also have vane diffuser. That means inside the diffuser you can have vanes. For example, you can have this kind of vanes. Okay, and these vanes can be fixed or adjustable. That means in the fixed case you cannot change the position of the vanes, but in an adjustable case you can vary the position of the vanes in the diffuser. Okay. This is a cut view of an actual centrifugal compressor. Again you can see the different parts here. Refrigerant enters like this. This is the eye of the impeller. Okay, then you can also see the impeller blades, and you can see the diffuser plates, and you have the vanes here. Okay, so this is a vane diffuser, and finally you have the volute casing here, and from the volute casing refrigerant, high pressure refrigerant comes out like this. So this is the single stage centrifugal compressor, and the diffuser is rotated by this shaft. You can see the shaft and it is rotating in this manner. Okay, and of course you have to have some sealing, and also a gland is used for sealing the compressor. Okay, so coming back to the diffusers, as I said, the diffuser can be vaned or vaneless, and vanes can be fixed or adjustable. Vane diffusers are compact compared to the vaneless diffusers and are commonly used for high discharge pressure applications. The size of these compressors using vane diffusers will be smaller, and generally they are used for high discharge pressure applications. Okay, that is the advantage of vane diffusers. However, vane diffusers has one disadvantage. The presence of vanes in the diffusers can give rise to shocks, as the refrigerant velocities at the tip of the impeller blade could reach sonic velocities in large high speed centrifugal compressors. So what happens in large high speed centrifugal compressors is the tip speed will be very high. Okay, once the tip speed is high, the refrigerant velocity at the tip of the impeller also will be high. Okay, and it may so happen that it is higher than the sonic velocity. Okay, so when you have this kind of a situation, a very high velocity supersonic refrigerant, when it enters into the vane diffusers, it produces a shock. Okay, so this is one of the problems of vane diffusers. Of course, there are measures to take care of the shock if it is not too high, but still this is a disadvantage, especially when you have very high speed centrifugal compressors. In vaneless diffusers, the velocity of refrigerant in the diffuser decreases and static pressure increases as the radius increases. So remember that the principle of diffuser, as I said, is to convert the velocity pressure partly into static pressure. Okay, how do you do this? How do you convert the velocity pressure into static pressure? You have to reduce the velocity smoothly in such a way that the velocity gets converted into static pressure rise. So in a vaneless diffuser, the velocity conversion takes place as the radius increases. That means the cross sectional area for flow increases. As the area increases, velocity reduces, and this reduction in velocity leads to increase in the static pressure. Okay, so this is the principle of vaneless diffuser. since the pressure rise and for a given pressure rise or for a given drop in velocity, you require a larger diameter if you are using a vaneless diffuser. As a result, the size of the vaneless compressor using a vaneless diffuser will be larger compared to a vaned diffuser compressor. Okay. So that is what is mentioned. As a result, for a required pressure rise, the required size of the vaneless diffuser could be large compared to vane diffuser. However, the problem of shock does not arise with vaneless diffusers, as the velocity can be diffused smoothly. So this is an advantage of vaneless diffusers, so you do not come across the problem of shock. Generally, adjustable guide vanes or pre-rotation vanes are added at the inlet of the impeller for capacity control. So this is about the diffuser. Now if you look at the inlet can also can have vanes, and these vanes are known as inlet guide vanes or pre-rotation vanes. And what is the purpose of these pre-rotation vanes? The purpose is to control the capacity. You can see that in this picture you have this is the inlet and you have the guide vanes here. Okay, so these are all the guide vanes, all these. Okay, and the position of these guide vanes can be adjusted in such a way that by adjusting the position you can change the flow rate, and you can also introduce a tangential component of velocity at the inlet. Okay, so this will kind of through this you can control the capacity of the compressor. Okay, so this is the purpose of guide vanes. Of course, you can also see the guide vanes here. So these are the guide vanes. Okay. So normally almost all centrifugal compressors use these guide vanes as a means of controlling the capacity. Okay, whereas the diffuser may or may not have vanes. Now let us look at the analysis of steady flow compressors. This analysis is a very simple analysis and it holds good for any steady flow compressor, not necessarily a centrifugal compressor. Okay. So, but we confine ourselves to centrifugal compressors in this particular lecture. Okay. And what we do in this analysis, we simply apply the steady flow energy equation to a steady flow device, that is nothing but the steady flow compressor. Okay. So from steady flow energy equation, so you know very well what is the steady flow energy equation is. So we have the, let us say that this is the compressor. Okay. So low pressure refrigerant at condition I enters into this compressor at a steady rate, and work of compression is supplied to the compressor, and as a result of which the refrigerant gets compressed and it comes out as a high pressure vapor. Okay. So E stands for the exit, that is high pressure vapor, and I stands for the inlet, that is low pressure refrigerant vapor. Depending upon the design and depending upon the operation, there can be some heat transfer from the compressor to the surroundings. Okay. So if you look at the energy flows, you have the energy flow by means of mass flow here and mass flow at the inlet and mass flow at the outlet, and you also have energy input by means of the work input, and the energy interaction between the system and the surroundings by means of the heat transfer rate. Okay. So this is the system and this is the control volume, and to this we apply the steady flow energy equation. So as you know, the steady flow energy equation is something like this. This is the rate at which heat transfer is taking place from the compressor to the surroundings, and M is the mass flow rate, HI is the inlet enthalpy, and this is the inlet specific kinetic energy at the inlet, this is the specific potential energy at the inlet, this is the work input to the compressor, and this is power input to the compressor if you are writing in terms of mass flow rates. So WC is the power input to the compressor, HE is the exit enthalpy, and V square by 2 is the exit kinetic specific kinetic energy, and GZE is the exit specific potential energy. So this is a simple steady flow energy equation which we have seen before. Okay. And if you assume that the potential and kinetic energy changes are negligible, okay, that means this is almost same as this and this is almost same as this, then we can drop these terms, and if you drop these terms, this equation becomes simply like this. Q, as I said, is the heat transfer rate from the compressor, and WC is the power input to the compressor. Okay. So in a centrifugal compressor, the heat transfer rate Q is normally negligible, as the area available for heat transfer is small. Okay, that means heat transfer rate is negligible compared to other energy terms. So you can neglect heat transfer rate. So once you neglect the heat transfer rate, the power input to the compressor is simply given by mass flow rate into enthalpy rise across the compressor, that is He minus Hi. Okay, so this equation is valid for both reversible as well as irreversible adiabatic compression, provided actual enthalpy at the exit of compressor is used in case of irreversible compression. Okay, that means this is for both reversible as well as irreversible. Okay, if you are using reversible, then this will be isenthalpic enthalpy and isenthalpic enthalpy rise. If it is irreversible, then you have to use the actual enthalpy at the exit of the compressor. Okay, that is the difference. In case of reversible adiabatic compression, the power input to the compressor is given by, as I have just now have explained, it is nothing but mass flow rate into a specific enthalpy rise for an isentropic process. This subscript stands for isentropic process. He, as I said, is the exit enthalpy and Hi is the inlet enthalpy. Okay, so power input is simply mass flow rate into He minus Hi. Okay, and using the thermodynamic relation TdS is equal to dH minus VdP, the isentropic work of compression is given by this. How do we get this? Since this process is isentropic process, ds is 0. Okay, so from this thermodynamic relation TdS is equal to dH minus VdP, we get that dH is equal to VdP. So work of compression, specific work of compression is nothing but integral dH, which is equal to this, and that is equal to integral VdP. This integration has to be performed along the isentropic process from the inlet pressure Pi to the exit pressure Pe. Though expression for isentropic work is same for both reciprocating and centrifugal compressors, the sources of irreversibility are different in case of actual compressors. If you look at the expression and if you compare this expression with the specific work expression that we obtained in case of reciprocating compressor, you find that the expression is same. Okay, in both cases we got the specific work for an isentropic compression as integral VdP along the isentropic process. Okay, so as far as the isentropic ideal compressors are concerned, the expression is same, but when you talk about the actual compressors, the expression will be different because the phenomena will be different in case of an actual centrifugal compressor and actual reciprocating compressor. Let us see what are the differences. In reciprocating compressors, the irreversibility is mainly due to heat transfer and pressure drops across valves and connecting pipelines. So what is the difference between an ideal isentropic compressor and an actual isentropic compressor? The difference lies in the irreversibilities. And what are the irreversibilities? If you remember, in case of a reciprocating compressors, the irreversibilities are mainly due to heat transfer from the compressor to the surroundings and from the compressor to the refrigerant or from the refrigerant to the surroundings. Okay, so this is an irreversible process and this causes irreversibility. In addition to that, we also had irreversibilities due to pressure drops across the suction and discharge valves and also across the connecting pipelines. Okay, so these are the major sources of irreversibilities in case of a reciprocating compressor. Now let us look at what are the sources of irreversibility in case of centrifugal compressors. In case of centrifugal compressors, the source of irreversibility is due to the viscous shear stresses at the interface between the refrigerant and the impeller blade surface. Okay. So if you look at the working principle of a centrifugal compressor, you find that between the impeller blade passages, refrigerant flows at very high speed. Okay. When it flows at a very high speed, and normally the impeller diameter is also large, so it flows for a considerable distance at very high velocities. Okay, and as it flows at very high velocities, there will be shear stresses at the interface between the refrigerant and the impeller blade. Okay, this is because of the fluid friction. Okay, so this causes irreversibility, and this is a major source of irreversibility in case of centrifugal compressor. As I have mentioned before, the irreversibility due to heat transfer is generally small in case of centrifugal compressors, because given the size and given the capacity, the heat transfer is almost negligible. Okay, so the irreversibility due to heat transfer is negligible. So major source of irreversibility is because of the viscous shear stresses. Okay, so this is the major difference between an actual centrifugal compressor and an actual reciprocating compressor. And in reciprocating compressors, the work is required to overcome the normal forces acting against the piston. So why do we require work input in reciprocating compressors? If you think about the working principle of a reciprocating compressor, when you compress, that means when the piston is compressing the refrigerant, it encounters a resistance by way of a normal force, and this normal force is due to the pressure acting against the piston. And what is the maximum amount of this force? This maximum amount of this force is equal to the area of the piston multiplied by the maximum pressure developed inside the compressor, and this maximum pressure is almost equal to the condenser pressure. Okay. So the work is required to be done in overcoming this normal force, which is equal to P condenser into the area of the piston. Okay. Whereas in centrifugal compressors, work is required to overcome both normal pressure forces as well as viscous shear forces. Okay. So here the refrigerant has to flow against a increasing pressure. So you have a normal pressure acting on the refrigerant. In addition to that, it also has to overcome viscous shear forces. Okay. So the work input is required for these two purposes. In case of centrifugal compressors, the actual specific work is larger than the area of PV diagram due to the irreversibilities and also due to continuous increase in specific volume due to friction. Okay. So if you have a PV diagram of a centrifugal compressor, you cannot find out the work input from the PV diagram because the area of the PV diagram does not give you the actual work input to the centrifugal compressor. You will find that the actual work input is always higher than the area of the PV diagram in case of a centrifugal compressor, and this difference is due to the irreversibilities, and it is also due to the fact that the specific volume continuously increases because of the fluid friction. Okay. And to account for the irreversibilities in centrifugal compressors, a polytropic efficiency eta pol is defined. It is given by the polytropic efficiency is the ratio of polytropic work divided by the actual work. So if you are writing in terms of specific works, this is nothing but integral VdP integration has to be performed from Pi to Pe divided by He minus Hi. So this is your polytropic work and this is your actual work. Okay. So this has got to be actual enthalpy rise. This process, as you know, the polytropic process can be written as something like this: PV to the power of n is constant. So all polytropic processes can be represented by this equation, and if you substitute this equation here, you can find out the expression for polytropic work here. Okay. So I am making use of this equation here. So you find that the expression for polytropic work is given by F into n by n minus 1 into Pi Vi into Pe by Pi to the power of n minus 1 by n minus 1. Okay. Now let me explain the terms. This F is a correction factor. This is a correction factor. This takes care of the variation of the index n during the compression. Okay. And this factor is actually negligible. It is found that its value varies from 1 to 1.02. Okay. That means the error will be maximum error will be about 2%. So most of the times you can neglect this, but if you are very particular, then you can include this term, and this term has got to be obtained from experiments, and this takes care of the variation of the index n, where n is, as you can see, is the index of the equation. PV to the power of n is constant. Okay. And Pi is the inlet pressure, that is the suction pressure, and Vi is the specific volume of the refrigerant at the suction condition, and P is the exit pressure or the discharge pressure. Okay. So these are the different terms of this equation, and as I said, this equation is obtained by simply integrating integral VdP from Pi to Pe. And if the refrigerant vapor is assumed to behave as an ideal gas, then it can be shown that the polytropic efficiency is equal to this expression. So under the assumption that refrigerant is behaving as an ideal gas, we can get a very simple expression for the polytropic efficiency in terms of the index n and gamma, and gamma, as you know, is the specific heat ratio Cp by Cv. Okay. So this equation is valid only for the ideal gases. Okay. So in case of refrigerants, as you know, which do not really behave as ideal gases, what is normally done is this gamma is replaced by the isentropic index of compression K. Okay, that means the polytropic efficiency is simply given by n by n minus 1 into k minus 1 by k, where n is the index of polytropic compression, k is the index of isentropic compression. Okay, so this is a simplification. Actual analysis is very complicated, but this is a generally practiced so that you can have a rough idea of the polytropic efficiencies. Okay. For actual centrifugal compressors, the polytropic efficiency is found to lie in the range of 0.7 to 0.85. As I said, this is obtained from experiments, and from experimental values show that the efficiency lies between 70 to 85%. The value of index n is obtained from actual measurements of specific volume at the inlet and exit of the compressor, and then using the equation PV to the power of n is constant. Okay. So, the actual process will be irreversible. So, you really do not know what is the path of the process. So, in order to find out this n, what is done is, now experiments are conducted, and you find the suction pressure and suction specific volume. You measure the suction pressure and suction specific volume, and you also measure the exit pressure and exit specific volume. Okay. So, you know PIVI and PV, then use the equation PV to the power of n is constant. That means PIVI to the power of n is equal to PV to the power of n, and PIVI and PV are known. So, from this you can find out the value of n. Okay. So, this is how the index n is obtained in practice. This procedure usually gives fairly accurate results for refrigerants made of simple molecules such as water or ammonia. For other refrigerants, errors could be considerable. Okay, so this procedure and the expression for polytropic efficiency and all is not a 100% correct method, or it does not give you 100% correct value. Okay, and it is obtained, it is found that it generally gives reasonably good results if you are talking about simple refrigerants made of simple molecules such as water or ammonia. Okay. Then this procedure is pretty good. Whereas for other refrigerants, for example, for other heavy synthetic refrigerants, this may give rise to errors. Okay. When refrigerant velocities are high, then change in kinetic energy across the compressor can be considerable. So far we have been we assume that the kinetic energy change across the compressor is negligible. Okay, but in centrifugal compressors you find that the velocities can be quite high, and the kinetic energy change could be quite considerable. Okay, so in some cases you have to consider the kinetic energy change, you cannot neglect it. Okay, so if you consider the kinetic energy change, how do you find the power input? The power input is simply obtained by this expression where WC is the power input, this is again the mass flow rate into the HTE minus HTI, and where this HTE and HTI are not the specific enthalpies, but they are what is known as stagnation or total enthalpies at the exit and inlet of the compressor. Okay, so when the kinetic energy is not negligible, you have to use you have to use stagnation enthalpies instead of static enthalpies. Okay, and these two are related by this expression. HT is the stagnation or total enthalpy, and H is the static enthalpy, and where V is the velocity of the refrigerant. Okay, as you can see here, when the velocity is negligible, HT will be almost same as H. That means the static enthalpy will be close to the stagnation enthalpy. The similar to stagnation enthalpy or total enthalpy, you can also define what is known as stagnation pressure and stagnation temperature. The stagnation pressure PT is defined as the pressure developed as the refrigerant is decelerated reversibly and adiabatically from velocity V to rest. Okay, and from energy balance you can show that so when you adiabatically, reversibly and adiabatically bring down the velocity from value V to 0, you find that you get this expression HT minus H is equal to V square by 2, and you get this expression again. To get this expression you have to use TdS is equal to dH minus VdP, and this is a reversible adiabatic process, so this is equal to 0. So dH is equal to VdP. Okay, so dH is nothing but HT minus H, so HT minus H is nothing but integral VdP along the isentropic process, and the integration has to be performed from the static pressure P to the stagnation pressure PT. Okay, and this is equal to V square by 2. Stagnation pressure and temperature of moving fluids can be measured by pressure and temperature sensors moving along with the fluid at the same velocity. So, if we want to find out the stagnation pressure or stagnation temperature of a moving fluid, only moving fluids have stagnation properties. So, if you want to find out the stagnation pressure or temperature, you have to have the sensors which move along with the fluid at the same velocity as that of the fluid. Okay. So, the measurements recorded by these sensors moving at the same velocity will give you the stagnation pressure and stagnation temperature. For an ideal gas, you can have assumptions. For an ideal gas, you can write Ht minus H. As you know, the enthalpies of an ideal gas depend only on temperature. So, Ht minus H can be written as Cp into Tt minus T, where Tt is the stagnation temperature and T is the static temperature. Here we are assuming that the Cp is constant, or you are using a constant average specific heat. Okay. So, you can write Ht minus H as Cp into Tt minus T, and this, as you know, is equal to V square by 2. So, from this expression you get an equation for the stagnation temperature Tt, that is equal to T static temperature T plus V square by 2 Cp. Okay. And you have to be careful about the units here when you are using Cp as kilojoule per kg Kelvin, and if you are using V as meter per second, then you have to divide this expression by 1000, okay, because only then the units will tally. So, you can see here that when the velocity is small, static pressure will be almost same as the static temperature is almost same as the stagnation temperature. Okay. And for incompressible fluids, that means for fluids which for whose density remains almost constant, you know that the integral VdP along the isentropic process, V is the specific volume which is almost constant. So, you can write integral VdP as V into Pt minus P, where Pt is the stagnation pressure and P is the static pressure. This is equal to V square by 2. So, from this equation you can get an expression for the stagnation pressure in terms of the static pressure P, velocity V, and the specific volume small v. Okay. So, this is how you can find out the stagnation properties, right, and as I said, the stagnation properties become important when the velocities are very high. Okay. Now, let us look at the selection of impeller speed and diameter, which is very important in the design of centrifugal compressors. How do we select these, and what is the relationship between these parameters and the performance of the compressor? Now, let us once again let us look at the working principle, and from the working principle we know that the stagnation enthalpy remains constant during the flow of refrigerant through the inlet, through the diffuser, and through the volute casing, as no external work is done in these parts. So, if you look at the refrigerant flow through the inlet, refrigerant flow through the diffuser, and refrigerant flow through the volute casing, in these three parts you are not adding any energy, or no, you are not removing any energy. Okay. That means the stagnation enthalpy remains same. Okay. Only thing that happens here is velocity will be converted into static pressure, otherwise the total enthalpy remains constant. Okay. Whereas in the impeller you are adding work input. Okay. So, in the across the impeller you find that the stagnation enthalpy is increasing. Okay. So, stagnation enthalpy increases as the refrigerant flows through the impeller, as external work is done on the refrigerant. Hence, to establish a relationship between the power input and the impeller speed and diameter, it is essential to find the torque required to rotate the impeller. So, the basic principle, as I have mentioned at the very beginning, is that you impart angular momentum to the refrigerant and then you convert the momentum into static pressure. Okay. So, work is required to impart the angular momentum to the refrigerant. So, we would like to find out what is the power input or what is the work input to the compressor. So, in order to find that, first we have to find out what is the torque to be imparted to the refrigerant. So, we first find the torque, and from the torque we find the power input. Okay. To find the torque, we have to look at the velocity diagram at the impeller outlet. Okay. So, this picture shows the velocity drawing, velocity diagram at the impeller outlet. Of course, this is I am showing the velocity diagram at the outlet, and here I am assuming that the refrigerant enters axially at the inlet. Okay. So, that means at the inlet it does not have any tangential component, it enters axially. Okay. So, this is one of the assumptions. So, you can see here that the impeller is rotating in this direction. Okay. So, this is the direction of rotation. right? And if you are drawing the velocity diagram at the tip of the impeller, that means at this point, you find there are different velocities. And what are the velocities? First you have what is known as the peripheral velocity or tip speed, that is given by u2, and that is nothing but this. Okay, so this is your u2, and what is this? This is nothing but the product of the rotational speed of the impeller in radians per second, this is in radians per second, multiplied by the impeller radius r2. Okay, so if you multiply the rotational speed with the impeller radius, you will get the tip speed u2. Okay, and you also have vr2. Okay, the subscript r stands for relative and 2 is the exit. So vr2 is nothing but the relative velocity, as you can see here, relative velocity of the refrigerant with respect to the impeller. Okay, and if this is the relative velocity of the refrigerant and if this is the u2 is the peripheral velocity of the impeller, then the difference between these two is nothing but your absolute velocity of the refrigerant, that is given by capital V2. Okay, so capital V2 is the absolute velocity of the refrigerant. This absolute velocity can be split into tangential component Vt2, this is the tangential component Vt2, and normal component Vn2. Okay, so this is the typical velocity diagram at the impeller outlet. So we have 4 velocities, that is the, let me repeat once again, you have the tip speed small u2 and absolute refrigerant velocity capital V2 and the relative velocity of the refrigerant V subscript R2, and then you have the tangential component of the absolute velocity V subscript T2 and the normal component V subscript N2, and this angle beta is known as the blade angle if you are assuming that there is no slip. I will explain what is the slip, okay, a little later. So this is the velocity diagram at the impeller outlet. Now how do we use this velocity diagram to find the torque, and from that how do we find the power input? The torque required, as you know, is equal to the rate of the change of angular momentum of the refrigerant. Okay, this is the definition of the torque, and assuming the refrigerant to enter the impeller blade passage axially, that means it does not have any tangential component at the inlet, the torque tau is given by this expression, where m is the mass flow rate, r2 is the radius of the impeller, and Vt2 is the tangential velocity of the refrigerant. Okay, so basically mass flow rate into velocity will give you the linear momentum, multiply that into the radius r2 will give you the torque. Okay, this is the rate of, since you are talking about the mass flow rate, this will give you the rate of change of angular momentum, which is nothing but the torque tau. Okay, now the power input to the impeller is simply equal to tau into rotational speed omega. Okay, so power input P, or I am using actually the capital W. Okay, let me stick to that. So capital WC is nothing but the torque multiplied by the rotational speed, that is tau into omega, and you substitute the expression for tau here. Tau is nothing but mr2 into Vt2. So power input becomes mr2 into omega into Vt2, and as you know, r2 into omega is nothing but u2, which is nothing but the tip speed. So finally we get that the power input for this particular case is given by mass flow rate into the tangential velocity component Vt2 into tip speed of the impeller u2. Okay. Now the volume flow rate from the impeller is proportional to the normal component of velocity. Okay. So the volume flow rate basically depends upon this. Okay, this is the normal component of velocity, and we have just now shown that the power input and torque depends upon this component. Now this component can be written in terms of the tip speed u2 and the normal component. How? This is nothing but the peripheral velocity u2 minus this. Okay, and this is nothing but Vn2 into cot beta. Okay, so this distance is Vn2 into cot beta. So u2 minus Vn2 into cot beta will give you Vt2. Okay. So that is what is done here. From the velocity diagram, the tangential component Vt2 can be written as Vt2 is equal to u2 minus Vn2 cot beta, and here you take the u2 as the common. Okay, so this can be written as u2 into 1 minus Vn2 cot beta by U2. Okay. So now you substitute this expression in the expression for power input. We had the expression for power input like this. So we are writing power input as m into U2 into Vt2, Vt2 we are substituting this expression. So finally this becomes m into U2 to U2 square multiplied by 1 minus Vn2 cot beta divided by U2. Okay. The objective of this is to finally correlate the power input and the pressure rise to the geometry of the impeller and the impeller speed. Okay, that is why we are doing these manipulations, right. Now, thus the power input to the compressor depends upon the blade angle beta, as I said. The blade angle will be less than 90 degrees for backward curved blades, this is important to remember, equal to 90 degrees for radial blades and greater than 90 degrees for forward curved blades. Thus, for a given impeller speed, the power input increases with the blade angle beta, because from the expression for power input you find that you have 1 minus Vn2 into cot beta by U2. Okay, so as beta increases, your cot beta reduces. Okay, once the cot beta reduces, the power input increases. Okay. Now let us take a simple case. As I said, the actual analysis of centrifugal compressor is very complicated. Okay, so what we are I am presenting here is a simple analysis. Okay, the analysis becomes simple if you assume that there is no tangential component at the inlet, and if you also assume that the blade is radial. Okay, once the blade is radial, beta becomes 90 degrees. Okay, so for radial blades, when beta is 90 degrees, the power input is given by this expression. So here beta is 90, so cot beta becomes 0. So power input is simply equal to m into U2 square. Okay, so we get a very simple expression which directly relates the power input to the tip speed. Okay, remember that this is only valid for beta is 90 degrees and with no tangential velocity at the inlet, right. And if you are assuming that the process is reversible and adiabatic, you can also write the power input in terms of the enthalpy rise of the isentropic process and the mass flow rate. Okay, that we have seen earlier. So power input is also equal to mass flow rate into isentropic enthalpy rise. So this, as we have seen, is nothing but m into integral VdP from Pi to Pe along the isentropic process. Okay, so if you equate these two equations, you finally find that the enthalpy rise for the isentropic process is linked to your tip speed U2 square, and tip speed is nothing but the product of rotational speed into the radius of the impeller. Okay, so that is how we link the enthalpy rise to the blade parameters. So we can also write, so we can also perform the integration, and we can if you perform the integration you get this expression, because for isentropic process, as you know, PV to the power of k is constant, where k is isentropic index of compression. So if you substitute that here, you get this expression. Okay, and this whole thing is equal to omega into R2 square. From this expression, you do a mathematical manipulation, a simple manipulation. You can show that the pressure rise, pressure ratio Rp, that is the discharge pressure divided by the inlet pressure, is given by this expression. Okay, and you can see that for a given inlet conditions Pi and Vi, and for a given refrigerant, that means let us assume that k is constant, you find that the pressure ratio depends purely on the rotational speed of the impeller and the impeller diameter. Okay, so that is how we established the relationship between the power and the pressure ratio with the impeller parameters. Okay, that is the whole objective of this analysis. Generally, from material strength consideration, the tip speed is limited to about 300 meter per second. Okay, this is a industry standard. Normally in industry they do not exceed these speeds. So this puts an upper limit, as I have already explained, on the temperature lift with a single stage centrifugal compressor. Hence, for larger temperature lifts we require multi-stage compression. For given impeller rotational speed and impeller diameter, the pressure rise also depends on the type of the refrigerant used. You have seen that in the pressure ratio expression you have Pi, Vi, and you also have K. Okay, all these parameters depend upon the type of the refrigerant used. Okay, let me give a small example. For example, for a single stage saturated cycle operating between an evaporator temperature of 0 degree centigrade and a condensing temperature of 32 degree centigrade, the required tip speed if you do the calculations, required tip speed from the expression is nothing but square root of He minus Hi along the isentrope, where He is the enthalpy at the exit of the compressor and Hi is the enthalpy at the inlet to the compressor, and in this case I am assuming saturated cycle. So Hi is nothing but the saturated enthalpy at 0 degree centigrade, and He is the enthalpy of the superheated refrigerant at condenser pressure, and the entropy same as the inlet entropy. Okay, so this you can find out from the refrigerant property tables, and if you find the properties from the refrigerant property table and substitute these values, you find that the required tip speed will be 145.6 meter per second in case of 134A, refrigerant R134A, and the required tip speed will be 386 meter per second in case of ammonia. So you can see that if you are using ammonia, the required tip speed becomes very large. Okay, so everything else remaining constant, you find that for ammonia you require very high tip speeds. In fact, this tip speed exceeds the safe limit or the maximum upper limit. Okay, so if you are using ammonia for these conditions, and if you want to use a centrifugal compressor, you may have to go for multi-stage compression. Okay, and if you can also calculate what is the required impeller radius if you are assuming that the impeller is rotating at 50 rps, and from the tip speed and the rps you can find out what will be the required radius. You find that the required radius in case of R134A will be 0.4635 meters, and in case of ammonia it will be 1.229 meters. That means for a given rotational speed you find that ammonia compressor, if you are using a single stage, will be very large compared to R134A. Okay. In fact, we will see later for centrifugal compressors we find that normally the high boiling point refrigerants are more suitable, okay, compared to low boiling point refrigerants. Similar type of analysis can be carried out for other types of blades, that means forward or backward curves, and also with a pre-rotation at impeller inlet. Okay, so you can extend this analysis by including beta. Okay, here we assumed radial blades, so cot beta becomes 0. So beta does not appear in the expression for pressure ratio or the power input, but you can include the beta for other types of. You have to include the beta for other types of blade, that means forward or backward curved blades. And if you have any tangential velocity at the inlet, you also have to include that in the expression for the torque. Okay. However, the actual analysis can be quite complicated if one includes the pre-rotation guide vanes slip between the refrigerant and impeller blades. In actual compressors, as refrigerant flows outwards along a rotating radius, a pressure gradient is developed across the flow passage due to the Coriolis component of acceleration leading to formation of eddies. Okay, I was mentioning slip. If there is no slip, then the angle beta is nothing but the blade angle, that is what I said. Okay, but what is this slip? This slip comes into picture because the refrigerant has to flow along a radius which is rotating at high speeds. Okay, this introduces what is known as a Coriolis component of acceleration. Okay, and this also introduces pressure gradient across the refrigerant passage. Because of this pressure gradient, secondary flows are induced in the flow passages, and this gives rise to what is known as eddies. Okay. For example, you can see here these are the eddies formed in the flow passages. Okay, and if you look at the pressure, you find that pressure on this side of the impeller will be greater than the pressure on this side. Okay, only then this blade can rotate in this direction. So here the pressure will be greater, and if you look at this side of the channel, you find that this pressure will be lower than this pressure, because this side pressure will be again higher than this pressure. That means there is a pressure gradient across the channel, and this pressure gradient gives rise to eddies of this form. Okay, the eddies are nothing but the secondary flows inside the flow passages, and you can see that the eddies rotate in an opposite direction. When the impeller is rotating in this direction, eddies are rotating in this direction. Okay, and because of the presence of the eddies, you find that the velocity at which the refrigerant leaves the impeller will be beta dash. Okay, whereas beta is the blade angle. Okay, so because of the eddy formation, you find that beta is greater than beta dash. Okay, these eddies rotate, as I said, in a direction opposite to that of the impeller. As a result, the actual angle beta dash at which the refrigerant leaves the impeller will be less than the blade angle beta. This reduces the tangential component of velocity, and hence the pressure rise. So what is the effect of these eddies? Obviously these eddies induce some losses, and because of these eddies you find that the actual tangential component at the tip of the impeller is less than the ideal tangential velocity. In fact, the ratio of the actual tangential velocity divided by the ideal tangential velocity is known as slip. Okay, so because of this slip, the pressure rise will be reduced. The pressure rise can be this effect can be taken care of by increasing the number of blades. That means by making the channels narrower. However, as you make the channels narrower, you find that the frictional pressure drop increases. So you have to make a trade off between the eddy formation and the frictional pressure drops and decide the number of the blades. Okay. So this at this point I stop this lecture, and we will continue this lecture in the next class, where we discuss the performance aspects of the centrifugal compressors. Okay. Now let me conclude briefly. In this lecture, the working principle and construction features of centrifugal compressors are explained, and steady flow analysis of compressors is presented, and a simple analysis to establish a relationship between power input, pressure rise, impeller diameter and impeller speed is presented. Okay. And as I said, we will continue this lecture in the next class. And before I leave, let me give the answers to the homework problem given in the last class. Okay. This is the homework problem given in the last class, and I have asked you to calculate the COP, enthalpy change, and the temperature of the refrigerant for the following three cases. First is the reversible adiabatic compression. The answers are COP is 6.98, enthalpy change is 46.15 kilojoule per kg, and the temperature at the exit is 78 degrees centigrade. And for reversible polytropic compression with N is 1.22, the answers are like this: COP is 7.09, enthalpy change is 39.72 kilojoule per kg, and the exit temperature is 67.7 degrees centigrade. And for the third case of irreversible adiabatic compression with index N is equal to 1.3, the COP is 6.15, enthalpy change is 52.36 kilojoule per kg, and the exit temperature is 87.9 degrees centigrade. Okay, thank you. Welcome back. This lecture is a continuation of the earlier lecture, wherein I introduced centrifugal compressors. In this lecture, I shall discuss the performance aspects of centrifugal compressors and briefly discuss the commercial centrifugal machines. Okay. The specific objectives of this particular lecture are to discuss refrigerant capacity of centrifugal compressors and how to control the refrigerant capacity, and discuss the phenomena of surging in centrifugal compressors, discuss the effects of operating temperatures and speed on performance, performance comparison with reciprocating compressors, and finally discuss briefly commercial systems with centrifugal compressors. At the end of this lecture, you should be able to explain how the refrigerant capacity of centrifugal compressors can be controlled, explain the phenomena of surging, discuss the effects of operating temperatures and speed on compressor performance, compare the performance with reciprocating compressors, and finally describe commercial systems working with centrifugal compressors. Now let us look at the refrigerant capacity of centrifugal compressors. For a given set of condenser and evaporator temperatures, the required pressure rise across the compressor remains same for all capacities large and small. That means if you fix the evaporator and condenser temperatures, obviously evaporator pressure and condenser pressure are fixed. So the pressure difference between the across the compressor also remains fixed. This is irrespective of the capacity. That means if you have a system working between 0 degrees evaporator temperature and 30 degrees condenser temperature, so whatever be the capacity, whether it is 100 watts or 100 kilowatts, the pressure ratio and the pressure difference remains fixed irrespective of the capacity. This holds good for any type of compressor.